In this video, we're going over how to solve polynomial and rational inequalities. Part of this is going to use the rational root theorem, so make sure you're comfortable with that concept before we start. And we're going to talk about a few different ways that you can solve these so that you can choose the method that you feel most comfortable with when you are faced with one of these problems. So this first one is a polynomial inequality. It has a degree 3. And even though it has 4 terms, I can see that I can't factor this using a grouping method or any other method that I know of besides rational root theorem, which is a way that we can factor when it doesn't use the traditional grouping or trinomials or any special cases. So with a rational root theorem, our first step is going to be to find P and Q, which in the definition of that theorem, P is the factors of the constant. So I'm going to list all factors of 4, and Q is the factors of the leading coefficient. And then to find our list of possible rational roots, we're going to do P divided by Q. You don't need to write any repeats, so as I go across, if anything shows up twice, I don't need to write it again. So it looks like we have 8 possible rational roots. Now keep in mind that these are only the rational roots, not irrational or complex, which all could exist in this graph. I can tell that there will be at least one rational root because we have a cubic function and odd power, and complex numbers and irrational numbers always come in pairs. So even if 2 of them were complex or irrational, there's got to be one that is rational. So we are going to find at least one of these works. If you've seen my video or any video on the rational root theorem, there's 2 approaches you can do from here. You can plug these numbers into the original function and check for zeros, but I don't like to start there because to me that's a lot of work to do. And even if you find something that is a 0, you still have to then divide to find the factors. So I just like to go straight to the dividing because if I'm using synthetic division, it takes about as much time. And if I find one that works, meaning I have a remainder of 0, then I already have the factors done. I don't have to do a second step afterwards. So I'm going to go straight into synthetic division. I always like to start with the 1s because if they work, they're really easy to work with. But you can start with any number on this list. There's 8 possible terms you can start with. I'm going to do 1 and then -1 if 1 doesn't work. So let's do this with synthetic. I'm going to go about this assuming that you know how to do synthetic division. So if you need a refresher, maybe pause here and find a refresher on synthetic. I can see because the remainder is not 0 that this is not a 0 of the function. So let's try -1. And I can tell that one's not going to work either. So next I'm going to move on to the next number in my list, which would just be 2. This one looks like it's going to work. So as soon as we get a remainder of 0, I now know that the 2 is a 0 of this polynomial, which means x minus 2 is one of the factors, and then this quotient is the other factor that the polynomial splits into. So now I can rewrite the original problem. Instead of a long cubic function, I can rewrite it as a factored linear and quadratic factor. Keep the inequality the same. And now, as soon as I get down to a quadratic, I'm going to find the zeros using a quadratic method instead of testing, because we already know quadratics can produce irrational or complex zeros, and this list that we had up top was only rational zeros. So don't continue to test. I can tell that this one is factorable, so I'm just going to go ahead and factor it. Cool. And then I see I have repeating factors, so I'm going to combine those together because no matter what step you do next, that's going to help. Okay, so from here I can tell that we have the following zeros. We have a repeating 0 at 2, and then a 0 at -1/2. You have 2 main methods of solving the inequality. We have a sign chart, which is a way to do this algebraically. There's a trick to make it fast, and you don't have to know what the graph looks like, or you can do it graphically. So if you're quicker at graphing the picture, then you don't need to plug anything in, which is also pretty quick depending on which one you're better at. Let's do the sign chart first. For the sign chart, we're going to put the factors that we just found in a column on the left side. And then I'm going to make columns for each of the zeros. I'm putting them in numerical order because I want to think of this bottom line here as a number line. So when I pick numbers in between, they should be in numerical order. And then we're going to test values on either side of -1/2 and 2. But before you start plugging things in, there is a shortcut to this. If you consider that this is in numerical order, so everything horizontally is working like a number line, -1/2 is where this factor produced a 0, and 2 is where this factor produced a 0. So if I were to plug in something that was smaller than what created 0, it should create a negative. If I were to plug in something that was bigger than what created the 0, it should create a positive. So I can fill those in pretty quickly, just knowing that there was a 0 at this stage, and then going left for negative and right for positive. Now the reason I skipped the top row is because it works a little different when it's squared. Anything that's squared, no matter what you plug in, will always produce a positive. So this one doesn't quite use that trick, but it is quick to fill in. What we're interested in is what the function's value is overall, because according to this inequality, we're looking for where the function overall is bigger than 0. So we're looking for anywhere where the whole polynomial is positive. The overall is just what is this whole function? Well, it's made up of these two factors multiplied together. So we're just going to go down each column and multiply together. So positive times negative is always negative. Positive times positive is positive. Positive times positive is positive. So now I can tell that my function is greater than 0 or positive when it is to the right of -1/2. So our final answer would be written as x is greater than -1/2, or in interval notation, which works really well with this number line, it's -1/2 to infinity. Like I said earlier, the second option is if you're quicker at graphing polynomials, then all you need is a quick sketch, and you can also see the same result. On the sketch, all I care about is the zeros and where the graph is above or below the x-axis. So because we have that multiplicity of 2, I know there's going to be a bounce at 2. The overall function is positive, so it starts up on the right, bounces at 2, and crosses at -1/2. So now just glancing at my graph, I can tell that it's greater than 0 in all of these places, which match up with that number line result. It's anywhere that's to the right of -1/2 or greater than -1/2. So either method is valid. The table method works really well if you don't know what the graph looks like, or if you're uncomfortable graphing it, which might especially be the case when we get to the rational functions. I know polynomials are pretty quick to sketch, so that might be the shorter method, is to graph it in this case, but you can kind of choose. They're both valid, they both work. Next, let's look at a rational function. One thing that is really tempting to do right off the bat is to multiply both sides by x minus 1. But you do not want to do that because you will actually lose a feature of the graph. If you remember, rational functions get vertical asymptotes from the denominator. It's where the bottom is equal to 0. And if I were to multiply by x minus 1, I might consider that to be a 0 when really it's a place where the graph is not defined. So instead of multiplying to get rid of your fraction, we actually want to keep it in place. And so the best method would be to subtract one of these two sides and combine them together. I'm going to move everything to the left to keep the x positive. So in the next step, I'm going to subtract the 2. And then we need these to be combined together in order to graph them quickly. So I'm going to multiply by x minus 1 for a common denominator. All right, and now we're ready to graph. Oh, nope, let's factor the top. Then we'll be ready to graph. All right, now we're ready. So at this stage, you're at that place where you get to choose, do I want to go the route of a sign chart or do I want to go the route of a graph? And it's completely up to you and what you're more comfortable with. Let's do the sign chart first. So with this one, we're going to put each factor, both things that create zeros and things that create undefined spots, and make those a row. And then I'm going to make the columns, again, based on all the zeros and those undefined spots in numeric order. So -1, 1, and 2, because again, I want to treat this like it's a number line in order to use that shortcut or to even plug numbers in between. I need to know what order they're in. So now I'm going to take each of these factors and mark where their 0 is. It doesn't matter if you put them in order or not. And then if I plug anything into that factor that is less than the number that created 0, it will create a negative. And anything bigger than that number would create a positive. You can do this slower by plugging numbers in and actually calculating whether they're positive or negative, but I really like that shortcut because it makes this method worth it. And then we need to know what's happening overall. Now in this case, we're not multiplying all of these together. We're doing a combination of multiplying and dividing, but whether you're multiplying or dividing, two negatives will always cancel, and a positive and a negative will always create a negative. So we can still use the same technique. As you work your way down a column, any two negatives would cancel each other out, and then you're left with a negative overall. In the next column, these two negatives would cancel each other out. In the next column, we've got a negative left over, and in the last column, it's positive. So now I'm going to go through and look for which sections match the inequality. So the inequality notation was less than 0, so we're looking for places where it is negative. And our solution set now would be anything to the left of -1 or anything between 1 and 2. And then we're going to look at it as a graph instead. So if you're more comfortable with graphing, we've got a vertical asymptote at 1, and we've got zeros at 2 and -1. We have a no horizontal, it's actually a slanted asymptote. So this one, I don't know if this is necessarily worth it. Let's find what this slant asymptote is. So it's just y equals x. That's not that bad. Okay, and then I'm just going to go ahead and sketch in the graph. And once again, we're going to look at our graph and check for where it is less than 0. So anything that is below the x-axis. Okay, and the solution set that I get is the same. It's anything to the left of -1 and anything between the asymptote at 1 and the 0 at 2. Now I want to go back and talk about that first step when you could have multiplied by x minus 1. What's going to happen in that case is that you're not going to see that there's this asymptote here, and you're going to end up with a partially correct solution. Like you might end up with this left side, but the right-hand side will do something funky and you'll be missing part of the correct solution. One other thing to keep in mind with these types of problems is the location of these asymptotes, especially if your inequality includes an equal to sign. So if I had just modified this problem to be less than or equal to, then even in my sign chart, I need to take a note that the 1 is an asymptote. And so everywhere else we could be equal to 0, which means that this bracket would turn to inclusive and this one would turn to inclusive. But anywhere where you have an asymptote, you can't equal 0, so that's going to be open still. So you have to be very, very cautious about the location of asymptotes in these, even if you're doing a sign chart. Even if you have no idea what the graph looks like, just be very careful about those verticals. All right, so that's everything you got. Let me know if you have any questions in the comments below. Thank you very much.